Thanks a lot, Jan. Good morning, everybody. So thanks to all of you to stay with me for so long. So as always, I will start in the middle of the last lecture where we stopped yesterday. So the last thing I showed you yesterday was this adiabatic or super adiabatic theorem for so-called non-equilibrium almost stationary states in infinite volume. So let me remind you what it is about. So the setting of the theorem is time-dependent infinite volume Hamiltonian, so actually a time-dependent infinite volume short-range interaction that for all time that depends smoothly on time and has a gap ground state for all time. And then we also add perturbation, phi, which is also an infinite volume interaction, and the perturbation V, which is of a special type, which is what I call the Lipschitz potential. So it's an external potential that satisfies the global Lipschitz condition. And the idea is that this could be, for example, the potential of a constant external electric field. Okay. We saw that such, if we define this Hamiltonian, the one with the gap ground state plus the one with perturbation, where we should add to the V also the phi, or could add, then we have two parameter Hamiltonian, H eta epsilon, depending on time, where epsilon controls the strength of the perturbation, and eta is the adiabatic parameter that controls on the microscopic time scale how fast the evolution, or how fast the Hamiltonian changes in time. So the smaller eta, the slower the change on the microscopic time scale, defined, for example, by the gap. Okay. So we assume that this derivation here of H naught has a gap, uniform gap of size at least G for all times. And as I mentioned yesterday, we in addition have to assume that also this gap ground state is a differentiable function of time. And as I said, if anybody is able to prove this in this context, that would be very nice. We would assume, as a conjecture, that also here it follows from the other assumptions, but we cannot show. But as I pointed out yesterday, we will not use it for our application. Or we will, in our application, it will be satisfied, it will not be an assumption. Okay, under these conditions, we prove what is called an adiabatic theorem. And the statement is that there is a near identity transformation generated by a smooth local interaction, infinite volume interaction. So again, this is something that acts everywhere, but locally. It's the sum of local terms. And by the automorphism generated by this interaction, we modify the ground state, the ideas a little bit of order epsilon and of order eta, such that for the full time evolution, this is this break U here. If we start in one of these states, in these super adiabatic states at time t0, and we evolve with a full time evolution, and compare this to time t, and compare this with the corresponding super adiabatic state at time t, then the difference is small if eta and epsilon are small in this sense. And we discussed this estimate in a second. So the idea is we can approximate the full time evolution by locally modifying the ground state a little bit. Okay. So this approximation has, I mean, there's several properties of this S which are important. One is what I already emphasized, is near identity. And now actually I see that I copied the wrong line here. This is only for the near, this is when this depends only on epsilon. This thing here will start with terms that are of order epsilon or of order eta or of higher order in both parameters. So this line is not correct. Sorry. So I should divide here by epsilon plus eta or something like this. So in the expansion of this guy, there will be terms that are also only of order eta. If you put epsilon to 0, if you have no perturbation at all, we're in the usual setting of the adiabatic theorem, and there will be terms of order eta. So, good. Correct this on the slide. Then the next thing I already emphasized and would like to emphasize again, this automorphism is determined by the transformation beta. Sorry, I call this automorphism also beta. I think I didn't introduce notation. I'm sorry. This transformation here is also called beta. This automorphism is at time t, depends only on the Hamiltonian at time t and its time derivative, but it does not depend on the history. So it's really local in time. And it's also stationary if the Hamiltonian is stationary, meaning that if on some time interval j, this Hamiltonian does not depend on time anymore, it's constant, then also this Athenaeus state, this approximation state, is constant over all this interval j and independent of theta. Okay, so whenever the Hamiltonian doesn't change, we get the stationary state. And in this situation, we call this state then non-equilibrium almost stationary state, because in general, it will not be expected that this is the ground state or the infinite volume or an eigenstate or equilibrium state of the Hamiltonian. And then we get from the previous estimate that from the proof that if we take this stationary state, which does not depend on time anymore, and we evolve it starting at time t0, and we could also put a j here, we could also do a j, this is the constant state. If we start with it, evolve it with a time evolution, as long as we stay in this interval where nothing changes, the state is almost stationary. So the errors we pick up are smaller than any power of epsilon. Here n is always arbitrary. So, and of course, these estimates hold as long as our observables are sufficiently localized. And the bigger the scale we look, the worse the estimate. Exactly. Omega depends, so to say, on where we are exactly. So we will later do the switching where we go from 0 to 1 to turn on a perturbation. Then there will be an interval where there's no perturbation. There we have a ground state, and then we have an interval, an infinite interval where the perturbation is turned on, and there it will be a different state. Sorry, say it again. Yes, yes. I mean, we should think of this omega here depending on time. Okay, but it depends on the Hamiltonian only locally, so it doesn't depend on the distance. It's a transformation of the instantaneous ground state using a transformation that is determined by the instantaneous Hamiltonian and derivative. So in a sense, I could, yeah, I mean, it's maybe putting here, I could also drop the j here and say it really depends only on epsilon if I know this constant Hamiltonian in this time interval. No, I mean, the idea is here, if I start in T0 with this state, then it remains constant. I mean, this is a special, I know it's still up there. This is a special case up here for intervals where the Hamiltonian is constant. I want to say that there, exactly. To highlight why we call it a near state. No, exactly. I mean, outside of three, I mean, maybe the notation was not good. I wanted to emphasize here that this is a state which is constant over the interval day. Then the point is there. Okay. Good. So in view of time, I will only make a few comments about the proof. And I should say that actually this proof is a adaptation of what is called adiabatic perturbation theory, which I describe, which is not my own theory, which I described in a book in 2004, which was my habilitation thesis. And there it was in the context of Schrödinger, semi-classical Schrödinger operators, and so on. But the perturbation theory is basically the same. And we had to adapt it to the certain setting. And this was possible because of this paper I mentioned already by Bachmann, Leroy, and Pratt, who first order adiabatic theorem for the extended many-body system in 2018. And the main input for me and also for them, and the main idea was to really use this quasi-local inverse of the Liouvillean constructed by Hastings. I explained to you last. So once you're able to do this, without destroying the locality structure, you can basically do the same algebraic perturbation expansions as the past. They assumed exactly they were in the situation where epsilon is 0. So for them, yeah. Here. They assumed no. I'm sorry. This is. They assumed no perturbation. They were in the standard setting, and they gave first order. But they also had to use this idea of inverting the Liouvillean, and this was this is where we learned it, and then I adapted it. There's a second ingredient, which is also used. Which also uses in the end this quasi-local inverse of the Liouvillean, a concept going under the name of orthomorphic equivalence of gap ground states, which I want to explain now in a bit more detail. For spin systems in finite volume, this concept was introduced by Hastings, and actually this is where he developed this quasi-inverse of the Liouvillean. He didn't call it that way, but this method was developed in these papers and then formalized in this paper by Bachmann, Michalakis, Mastragana, and Zim. And all of this, what they do and all of this here is done in finite volume, but with estimates, with error control that is uniform in the volume. And now, for us, we're working always in infinite volume because we don't want to assume that we can have finite volume approximations. We have to do also this part here in infinite volume, and this was done in a paper by Moon and Ogata in 2020. And I would like to show you briefly what this is about and why this is important for the proof. Because this is a concept which has become very popular independently of this adiabatic theorem. So first, the definition. What does it mean for two states in an algebra to be orthomorphically equivalent? So, or this is now really a specific definition for this quasi-local algebra. They are orthomorphic equivalent if there exists time-dependent, smooth, short-range interaction, such that the evolution it generates, the co-cycle it generates, intertwine the two states. Okay? So basically, if we can go from one state with smooth local deformations to the other state, that's called orthomorphic equivalence. And why is it important for us? You remember when I introduced the motivation, the adiabatic theorem in the standard setting and the proof of Kato, I told you it was important in the proof to write the change of the ground state also in terms of some sort of Schrödinger equation, of a dynamical equation, which was just the parallel transport equation. Okay, now the question is, what reflects replaces the parallel transport equation in the infinite volume setting. And what Moon and Ogata proved is basically a version of the parallel transport equation in infinite volume. And we gave a adaptation to fermionic systems, which is non-trivial, and I'll talk about this in a second. So let me first explain what they said. So given a Hamiltonian H0, satisfying the regularity assumptions are also made in the adiabatic theorem. I make them because I want to apply this result. Okay, so with a smooth gap ground state. Then the derivative of omega, which exists by assumption, satisfies this differential equation given by composing it with the Liouvillean generated by a quasi-local interaction, which is this I operator, this inverse of the Liouvillean, applied to the derivative of the Hamiltonian. Okay, basically this P operator, which was the commutator P dot P, is replaced by this operator. And this was observed actually in finite systems already by Hastings and Bachmann et al. But to prove this in the infinite volume turns out to be much more difficult. Okay. And so put differently, if we look at this interaction here, and it's the co-cycle it generates, that it intertwines the ground states at different times. So this is the parallel transport for these ground states. So in the original papers, the message was, if we have a gap Hamiltonian and change it continuously without closing the gap, then the corresponding ground states are automorphically equivalent. So that was then used to define gap spaces of matter and so on. So this is really has turned out to be a very popular and important concept. Good. But we also use this in the adiabatic theorem, much in the same way as it was used in Kato. We need to compare the time evolution of our approximate super adiabatic state with the true time evolution. And so we need to know how omega t, what the derivative of omega t is. Okay. So as a corollary of this result, actually, go the other direction of our result here for fermions, we found a very simple and straightforward proof of the so-called Goldstone theorem. The Goldstone theorem, you have probably heard of this in QFT, says that symmetry breaking of ground state, a ground state that breaks the continuous symmetry, always has never a gap. It's never a gap. So breaking of continuous symmetry is associated with gapless excitation, so it goes from both. Okay, and here we prove basically a version of this theorem, which is the contraposition to be exact. That if you have a gap ground state, then it has all the continuous symmetries of the parent Hamiltonian. I should say, if in the operator setting, if you assume you have a unique ground state, and then it is trivial that it has all the symmetries of the Hamiltonian. Surprisingly, this is not the case here. But it follows easily from this automorphic equivalence result. So the statement is given a short-range interaction with a gap ground state, and now assume that it has some continuous symmetry generated by something which is also sum of local terms, so local interaction. So beta is the family of automorphisms that commute with the Hamiltonian, and it has to be continuous. Then the ground state is invariant under this symmetry. That's the thing. How do you prove this? Very simple. Define the time-dependent family of Hamiltonians, which is just constant in time. We know that H has for each time a get ground state, omega, which is also independent of time. But then we just apply the previous theorem that tells us that this, and in particular, the ground state is constant, so it satisfies all the differentiability assumptions. But this tells us, the previous theorem tells us that the co-cycle generated by this operator satisfies that we commute sorry, now I have to be careful, maybe I mixed up the beta. So beta is the symmetry. So we want to show that omega alpha is the ground state. Alpha is the co-cycle intertwining the different ground states, and we don't define again, we define this time-dependent family of states for which we would like to show that it's constant. Okay? And they are ground states of the time-dependent family of interactions HT, which a priori are also composed with beta, but we know that HT is symmetric, is invariant under beta, so the corresponding family of parent Hamiltonians is constant. Okay. So, but now we have the explicit time dependence for omega 0, for omega t here, because we know that beta is generated by such an interaction, so we can easily check that the symmetry, the regularity assumptions of this family omega t is satisfied. And now we apply the previous theorem and show that this omega t and omega f are intertwined by this map alpha st generated by this guy. But the generator h dot is 0. This implies that alpha is the identity, and this implies that these two states are the same for all t and f, and this implies that omega is invariant also under beta. Okay, sorry for messing this up. Okay, so it looks like a trivial proof, and it's basically trivial once you have this this automorphic equivalence, the statement from the theorem. And I just very briefly, how did we come up with this? Because as far as I understand, and I talked to many people already in this field, nobody ever used this automorphic equivalence statement to prove Boltzmann's theorem. Why did we bother doing this? The reason is when you try to generalize results for thin systems to fermionic systems, the usual idea is, okay, we just restrict to even observables and then everything is the same. But if you try to generalize their proof to even observables, you have to realize that what you need an additional assumption. You need the assumption that also your ground state is actually, we even needed that our ground states are gauge invariant. So our current Hamiltonians are gauge invariant, commute with a number operator. You would think, okay, then also the states are gauge invariant. But how to prove it? Initially, I thought, okay, that should be a simple exercise, but we couldn't find the proof. But we also didn't want to assume it. So we came up with a different proof from Moon and Ogata, I mean, different in some parts, that works even without assuming that the ground states are gauge invariant. But then we realized afterwards, using that result, we can a posteriori really prove that if our Hamiltonian is gauge invariant, So this is the continuous symmetry. Then also the ground state dimension. So this is how we come up with this. And of course, I mean, I'm taking a bit of time here and also time in preparation. There have been proofs of Boltzmann's theorem in infinite volume string systems, but this is first. Absolutely, but for these techniques to work, we assume that this was to say in the definition of these spaces here already, that the operators are gauge invariant. Otherwise, yeah, things would look very different, and not all the results. I guess many results would not be correct. Okay, good. So this was the end of the third lecture. Now let me go to the last part. Okay. So now I would like to show you what I consider the main result, as far as how we get this Ohm's law for the Hall current response using these results. So this was the again this result I just showed you, because we will use it again. So I put it here. So this was so what we started out to do for this adiabatic switching process, we had special form of time-dependent Hamiltonian, namely the Hamiltonian of our system in equilibrium before we perturb it, H naught. There's no reason to assume that it's time-dependent. And then we switch on a perturbation in a time-dependent way with a switch function f. And the idea was that f is smooth, is 0 for time smaller than -1, and is 1 for positive or non-negative time. So it goes smoothly from 0 to 1. And now, in this specific case, the ground state of H naught is constant. So our regularity assumptions, which we can in general not prove, are trivially satisfied. So we don't have to assume them here. And we can apply the previous theorem to this specific setting and get as a corollary that if we look now at positive time, where the Hamiltonian is constant, there exists a state that is the state which I now call omega epsilon, and in the following, so to say, this near state for all positive, for the interval of positive time, such that if I start at okay, sorry, I should have I rescale time here by this definition, so I should put here just a -1, not a -1 of the eta, but that also works actually. If I start at time -1, where the perturbation is not turned on, in the state omega evolves with the time evolution, then for all positive times, I will be very close to this near state, up to terms that are smaller than any power of epsilon. And I can do this uniform in a certain range of adiabatic parameters. So forget this eta here, but the evolution still depends on eta, how fast I turn it on. I can do this as long as eta is not too small to compare to epsilon and not too large compared to epsilon. If I switch too fast, I will not be in the adiabatic regime. I will not end up in this near state. That's clear. I mean, if I do a very fast switching, dynamically many things can happen. So I have to do it slow. But if I do it too slow on a time scale that is smaller than any power of epsilon, I'm switching so slowly that this near state, which is almost always, which I think of a many-body resonance, will have enough time to decay. So I have to do the switching on a time scale so that my resonance state does not decay, but still adiabatic. And indeed, as a corollary of the previous result, you can convince yourself that if you pick Eta in such a fixed interval, you will find a constant so that this is uniformly for these eta smaller than -9. So that's the idea. And this result we now take as justification for using this state into which the system will develop for computing the current response of the system to this kind of perturbation. Okay, so the question was, how do we even compute the current response to a given perturbation? And the answer is, we do it in the near, because almost no matter how we drive the system into the perturbed state, we will always end up in the state omega f, which, by the way, is independent of f. It's independent of the history how we switch. It's independent of eta, of the speed of switching for eta in a large range of time steps. No, the independence on the left is, this was basically Jan's question yesterday, why does this approximation not depend on n? By a almost trivial resummation, this object here is no longer n-dependent. So basically, you can think of this being constructed n-dependent, and then we pick here n as a function of epsilon, so that this is satisfied here for all n with the same state. I mean, this is important. If this would depend on n, that would be a much weaker result. That we get exactly this power. I mean, if we would use finite range or exponential interactions, we would get here a power d plus 1. So basically, we get this worst power because we use interactions that decay faster than the polynomial and not exponential. Yeah. But we somehow thought that I mean, the formalism I showed you about these A infinity and B infinity spaces, I mean, this principle not really new. I mean, similar ideas were around. The way it was written there, we developed it, and it turned out to be, I think, many of the arguments, if you compare Monogatha to us, I would say our arguments are easier to read because working in these Cauchy spaces is very simple. While in working with exponential or stretch exponential and whatever, you have to, in the end, things look much more complicated. So, yeah, but it's important that this is an exponent that does not depend on n. Okay, now to finally come to conductance and conductivity, I just remind you, we have to decide what kind of perturbations we would now like to add to our system. And I will discuss two situations, or in particular, because in the literature, many others discuss this situation also, which is adding just the potential step. Okay, so adding a characteristic function on a half plane to the system. And the more physical thing, as I tried to convince you, is just adding a linear potential corresponding to a constant electric field. And then in this situation, I mean, for both perturbations, we can now construct the corresponding near. And in this near state, we then compute the current along this line, the current expectation along this line, or here, the current density in the x2 direction, because the field goes in the x1 direction. And we are interested in the whole response. One direction. And as I said, we expect at least that adding a small small shift in the chemical potential in one half plane does not close the spectral gap. For systems that are close to non-interacting or weak interacting systems, we can even prove. But adding such a perturbation does close the spectral gap. So the point is, in this situation, if we assume in addition that the gap does not close, we can apply the standard adiabatic theorem. never come to this. This is what other people did. Here, we cannot do this. We apply the neo-algebraic theorem. So let me give the first result, which is about adding a characteristic function on a half plane. So this is our perturbed Hamiltonian. We now know we can construct the corresponding Néa state, the state into which the system goes starting from the ground state when turning on lambda 1. And what we show is, yes, this was on the previous slide. I'm sorry. Maybe there. It's the sum over, it's so to say, the number operator in the right half plane times epsilon. The other one is really an external linear potential in the one direction. Okay, and then what we compute is the current flowing into the upper half plane. So the idea is we measure this current along here by computing the current flowing into the upper half plane. This is this I2 operator, which is just the commutator of H2 with the characteristic function on the upper half plane. This is the current flowing into the upper half plane. You can also think about the time derivative of the charge in lambda 2, that was flows into lambda 2. The characteristic function of the upper half plane. And, but this thing here, we have to compare to the current flowing already in the ground state. Because it turns out that even in the ground state, there might be microscopic currents already flowing along that line. And what we really want to compute is the difference between the perturbed and unperturbed situation. And what we show is that this is linear in epsilon with a number which is the whole conductance by definition, this linear coefficient, up to terms that are smaller than any power of epsilon. And this object here is given as the expectation in the unperturbed ground state of the commutator of lambda 1, lambda 2 off diagonal. Well, this is exactly the off diagonal map I introduced before. Okay? So, although lambda 1 and lambda 2 are not elements of the algebra, I mentioned that we can apply this map also to interactions. So this is and what I would like to emphasize here is that in this result, no periodicity homogeneity is assumed. Only the gap, nothing else. So whatever it is, if you have a gap, this result will hold true, and the number you get here will be the same independent of the choice of origin. So now I took very special half planes, right half plane, upper half plane with respect to arbitrarily choosing Cartesian coordinates. If you shift the origin around, that number will not change. It will be exactly the same. Actually, also if you change the orientation of the half plane arbitrarily, it will not change. It will always be the same. Of course, this is in the statement, and this is only if epsilon is small, then we get this linear term and we can forget about the rest. So, this is what I try to emphasize. We don't assume periodicity of the Hamiltonian of the state. There's no translation variance at all. There's only the gap. But this is basically the astonishing, surprising topological thing. So actually, I should say this commutator here is really an element of A infinity. So it's a very well localized level. Otherwise, we could not evaluate omega on it, which is not obvious because each term itself is not, but the commutator is. And this is what in at least in the non-interacting physics community, people often call a local churn marker. That is a local observable whose expectation gives you the churn number, which is, or in this case, here just the whole conductance, the index of this gas state. And no matter where you put this observable, I mean, this operator here depends on where you are, but the expectation is always the same. So the whole conductance is always the same, defined in this way. And what I would also like to say, if we could show, like for perturbations of non-interacting systems, that omega epsilon is really not only a near state, but it's the gap ground state of H epsilon, because the gap doesn't close by this small perturbation, then the proof actually shows that the response is exactly linear. These terms, and I will show you the proof in the other case, you will see. If I knew that the gap doesn't close, I could drop. I mean, for all epsilon that is such that the gap doesn't close, I have this exact relation. As I said, if you start from a non-interacting system, it does. In general, no. They really look at perturbations of non-interacting systems. So basically, as a corollary, I didn't write this down. We also didn't write it in the paper. Maybe we should. We have that in non-interacting systems, the response is exactly linear for small enough epsilon. Okay, even more. We could, I'm not going into detail showing this picture. You don't even need half plane. You take any characteristic function on any set that contains a cone. This is this blue thing here. And is 0 outside of a shifted cone. So that looks like this, but it just has a more complicated boundary. And then you measure the current into any other type of set which contains a cone, the green one, so that the cones are related like this. You get the same result. So this is a bit reminiscent of what usually people analyze when they look at Bulk boundary correspondence. If you we could think of this potential set like a sort of artificial boundary in the system, but where the gap doesn't close, but still we see a current along the boundary, independent of the shape of the boundary, that is always the same, that is almost linear or probably even exactly linear in the height of the potential set. So this is a very universal general response. Whatever you do when you increase on a certain set that is infinite and contains such a cone, the chemical potential, you will see always the same time flowing along the boundary. Okay, I'm not going to prove this. I'm going to show you a proof of the result which I think is more relevant, the one with the perturbing by the constant electric field. But the proof idea is very similar. But this result up to now, we published only for translation invariant systems, because now we want to compute the current density. And to compute the current density, to show that it exists, we use translation invariant. So let me just briefly tell you what we mean by a translation, because this is a very weak concept of translation. So in particular, magnetic systems with irrational magnetic fields are translation invariant in that sense, while they are not translation invariant in the usual sense. So what do we mean? Map P taking ZD to automorphisms of the algebra, we say it's a translation. So this is a map that takes the shift vector gamma to an automorphism on the algebra. If any set M is shifted when we shift by gamma, the gamma shift acts on the algebra over any set M as a map, as an automorphism to the algebra over M plus gamma. So operators here are shifted to operators here. But within this algebra, anything can happen, so phases and whatever. And the second condition is that the number operator on X is really shifted to the number operator at X of gamma. But it still allows for arbitrary things. Here? Oh, yes, I should. Okay, I mean, these are linear operators. I adopt the convention that the linear operator, linear map. I didn't do this all the time. I mean, okay, I didn't, at least, I got used to thinking of an automorphism as a linear map on the algebra, and here it's really applied to a set. That's why it's the image of the set, and okay, but yeah, it's a question mark. Yeah, in particular, we do not assume, and it will not be true in general, that this is a group homomorphism. Okay, because this is what you not get, for example, from magnetic translation. On the number operator, it will be a group homomorphism, but not an other operator. Okay, and then we define in the obvious way that a space is translation invariant with respect to some translation T, if it's invariant under T, and the Hamiltonian interaction is T invariant if the automorphism commutes with a corresponding derivation. Of course, having said this up here, I probably should also drop this first. I mean, it can do crazy things. For example, it can map, for magnetic translations, it will map a creation operator at X to a creation operator at X plus gamma times a phase. And if this phase doesn't satisfy some co-cycle condition, you will not get a group homomorphism. But it will still map an element in the algebra over AM to an element on the algebra of M plus gamma. Okay, and then the corresponding theorem is the following, that if we assume that H naught and our perturbation, phi, this bounded part of the perturbation, are periodic with respect to some T translation satisfying this, and we assume that H naught has a periodic gap ground state omega 0, then the corresponding near state for the perturbation where we now take something bounded, and the linear potential satisfies that immediately that the current density in the direction of x1 vanishes to all orders, and the current density in the direction of x2 is again nearly linear in epsilon, with a coefficient which is now the whole conductivity. I use sigma for conductivity and C for conductance, which is given by, again, average of an interaction, which is given by the commutator of the off-diagonal parts of position operators, now up to very small terms. And we, in particular, of course, also prove that the two coefficients, which are a priori different, are the same. Now here, the current operator in the K direction is just the commutator of H with the position operator. That's the standard definition, motivated by the continuity equation. And this bar denotes the average. So we can restrict every, always now in interaction, we can restrict it to some finite set lambda by dropping all the terms outside lambda. Then it's an element of the algebra. We compute the expectation, divide by the volume, and take the limit along any van Hove sequence and get the same result. And this is simple, that this exists. This is simple consequence of translation then. Yeah. 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 Exactly. Mm-hmm. Okay, you could try to do this. We could, you could, I mean, that would lead to the same. I mean, in the second part, you would have to measure the current density into the upper half plane. Okay, and actually, I will show you a corollary which will connect the two actually. Um, Somehow, okay. I mean, this was the first result we had because this is what people also like to do in the non-interacting setting if they can do it. And because it tells us something about the current density in space. Of course, I could put here measure with a lambda 2, and then I would, of course, I would get again infinity. This would never be, as in the other case, something finite. So I would have to average over a horizontal line. That would also give the same. It's possible to get a third theorem, and I will show you another theorem, maybe not a theorem, but a statement which is a theorem, that maybe goes in the direction what you mean. So before doing so, let me emphasize that in particular, this weakly interacting Hofstadter model is a model that satisfies all the assumptions. So we can apply to the standard model of the integer quantum Hall effect, I would say. Okay. This means non-interacting Hofstadter and then add weak translation invariant interactions, like think of a weak pair interaction or anything that is translation invariant. So actually, somehow you can add as much interactions as you like, as long as you don't close the gap. Then the theorem holds. But this is known only for sufficiently weak perturbation. And I will say something about what one expects when the interactions are very strong later this afternoon, probably. Okay, before I come to the consequence, which you just mentioned, I would wanted to give a sketch of the proof, and maybe I will do it in the 5 minutes because it's really very simple in the end if you forget about all technicalities. So how do we compute this current response? So let me just remind you. So what we want to compute here is the average of this current operator J2, which is given as this commutator. So this is a commutator of two interactions, which is again an interaction. Okay. And I drop the I and so because I don't want to write too much. So how do I compute this average in the case of periodic operators? I told you that I can write interactions also in the zero chain form as a sum of local terms, position, and axis. For a translation invariant interaction, all these local terms are the same, or let's say are translate with respect to a translation of each other, as you can easily see. So it's very straightforward to prove that this average actually can be computed by just taking the value of the Hamiltonian at 0, because all other guys are translate, and omega was assumed to be translation invariant. So omega epsilon is also translation invariant, that we have to solve, but that's easy. So we can just evaluate omega on this expression at 0. So better we take the Hamiltonian at 0 and commute with x, because x itself is not translation invariant. Sorry, this should be a k also. I want to treat both directions the same way. Okay, this should be not 2, but also I can take either 1 or 2 dimensions. Okay. So That is the first step. That's not difficult. Then, I'm sorry, take it to whatever. You can also put one here. It should be consistent. Then you remember that we found that in commutators, we could put an off diagonal on one part of the commutator, and this we actually can do also for the derivation generated by x. This is an additional statement one has to prove, because this is not a standard interaction, but we can do it. And the second part is now we did this off diagonal construction for gap ground state. Now I do this claim, I can also do this for these near states. I will show you in a second how, because this is very simple. Let's assume that we can do this also here. Then, and then the observation is, and this is something which is also well known in the non-interacting case, if you take the off-diagonal part of the position operator, then the off-diagonal part is actually now periodic again. So all the linear growth is in the diagonal part. The off-diagonal part, you can show this thing is now a periodic observable again, a periodic interaction. So we can exchange the role of the two, and again, by not localizing h at 0, but x off diagonal at 0 and commuting with h. So these are, of course, manipulations you have to show. But once we are here, we are almost done. Now we have this commutator with LH0 and epsilon here, so we replace H0 by H epsilon, meaning we add epsilon x1 and subtract the derivative with respect to epsilon x1 again. So we add it here and subtract it again. Now we use that omega epsilon is the near for LH epsilon, so that is invariant under the dynamics generated by epsilon, H epsilon up to terms of this order. So this is the result, the fact that we took a near. So actually in the proof, we don't have to know anything about the specific construction. We don't have to expand the state to all orders to get this. We just have to know that omega epsilon is an H epsilon invariant, almost invariant state in the step. And then we are left with this. And now we can, by the same argument as up there, also put an off diagonal on the x1 field. And this is what we wanted to end up with. Now we write this again, since everything is periodic as an average, and forget that we restrict it to 0, and we get the desired result. Up to one thing, in the claim, in the theorem, there was no epsilon here, there was the omega 0. And this is now the last thing for the moment. This is simple computation, although it took us quite long to understand this, because in the beginning we really tried to expand omega epsilon, and that's horrible. Instead, this gives us this expression very directly, and now the last step, and the end also mathematically the most difficult one, is to show that this expression does not depend on epsilon, that it is constant in epsilon, so we can continuously deform epsilon to 0. And about this I will talk later on. And then we realized that actually it's not only it's independent of epsilon, but actually this double commutator formula is in a sense invariant under all locally generated automorphisms of the algebra, not only the one generated by the superadiabatic transformation, but really constant within that space. Yeah, I'll show you later how to do this. Thanks a lot. I cannot explain it again because I did not explain it, I think. Let's say in non-interacting systems, particularly in periodic, non-interacting systems. One relates, and this was the insight of Fowler, got a Nobel Prize for this, was that you can relate the whole conductance, similar expression like this, to the Chern number of the block bundle. And that is one reason why I guess people call it topological. And it's a bit, sorry? Well, there are no block bundles here. Only in the Hochstadter model, I told you, in this butterfly, the colors you saw in the butterfly are exactly Chern numbers of the bundles defined by the spectral projection below the point where you get the color. But this is only for rational magnetic fields well defined. This as a Chern number of complex vector bundle over the torus. And if you never heard of Chern numbers, so just to give you a simple idea why this is also called topological is the corresponding result, which is better known, is the the theorem that tells you that if you have a closed two-dimensional surface in R3, then you can, so if you integrate the curvature of a closed surface in R3, like think of a sphere, this is a topological invariant, and actually it's related to the Euler number, to the number of poles in your Gauss-Bonnet. Thank you. I didn't remember Gauss. That's everything. Yeah. Gauss-Bonnet. It's very similar. You can think of it a bit like a complex version of Gauss-Bonnet. That if you integrate the curvature, in this case, the very curvature over this complex bundle, then you get an inverse or a multiplier. It's like Gauss-Bonnet, and that's why it's topological. And maybe it's also called topological, but because the idea is that everything is exactly invariant under smooth deformation. So what I will show here is that this number here is exactly invariant under locally generated automorphisms of the algebra that don't close the spectrum. That sense is again a topological quantity characterizing a whole open space of systems. Here I defined the boundary measurement. Maybe I take this picture here. I measure the current flowing along the boundary by taking another region, this is the green region, and computing the current flowing into this transversal region. Because I don't really know where this flows, I can show that this is a step. Then the current will be localized around the step with fast decay, faster than any polynomial, but I don't know where it flows exactly. It may also change. I mean, here it's not. In some regions it might be a bit more expanded than in others. So how I measure it? I measure just the total current into a transversal region. And it doesn't matter how I pick this. If I pick here, I could here also pick the upper half plane instead of the green thing, or something else. That just has to be transversal in a certain sense to